Our first speaker is Edoardo Rivello, who got his PhD from the University of Torino in 2010 and has been funded by the European Science Foundation for visits, among other places, here in Cambridge.
Yes.
He's working on theories of truth, and he will speak on self-determined sets of sentences.
Thank you. So, in the literature about formal theories of truth, very often we find an example like the one displayed on the slide, in order to assess if some formal theory of truth agree or not with our intuition about truth. For instance, I displayed an example due to Gupta, but in the simplified version of Visser. There are just three sentences, and the following informal argument allow us to assign the right truth value to each sentence. So phi1 and phi1 and phi2 contradict each other, hence they cannot both be true. But this is exactly what the sentence phi3 says, and so phi3 is true, hence phi1 is true and phi2 is false. And from this fact, Gupta uses this fact, this informal argument, to conclude that since the famous Kripke's formal theory based on least fixed point doesn't capture this example, then we have to reject Kripke's theory of truth. Of course, we can or we cannot agree with the conclusion of Gupta, but there is a very, very strong and almost general agreement about the informal argument, about the fact that this example has just a right assignment of truth value. So my starting question is why the informal reasoning about Gupta's example is so compelling, and also about many other kinds of examples like Gupta's. And the general intuition is that when carry out an informal argument like Gupta's, we are in fact using the general principles about truth that in the case of the full language are inconsistent due to well-known phenomena like the liar paradox, but that in the case of a restricted set of sentences like Gupta's example can be freely used. And the goal is to formalize this intuitive idea of a right assignment of truth values for some set of sentences, and then with respect to this formalization to identify classes of sets of sentences, so-called examples, which admit a right assignment, and then to understand the current formal theories of truth in terms of a fixed point or division theoretical processes as strategies to find the right assignments. And finally, to provide a standard partial interpretation for the truth predicate, which can capture this, the example so defined. And the purpose of this talk in particular is to illustrate something that we can do on this direction, just by using Gupta's example as a case study. So let me just fix the mathematical setting. So as usual, we fix first order language augmented by a unary predicate T, and we also fix a ground model, just a first order structure for the language L. And we assume that all sentences of the expanded language T are also object of the domain of the structure. And then we can define the Tarskian operator. We, for technical reason, we identify possible interpretation of the unary predicate with their characteristic function. And then we can define the Tarskian operator gamma for each total function h, we get another total function defining that gamma h of sentence phi is true if and only if the sentence is true in the expanded model in the standard model theoretic Tarskian notion of truth in a model. Of course, this works for any unary predicate T, and to say that T is a truth predicate means that ideally we want to find an H which is a fixed point of the Tarskian operator. Since in this case, when a sentence is evaluated true by the Tarskian operator, this is already true in the interpretation H. But of course, due to the liar paradox, there exist sentences like the liar sentence for which this is not possible, and so there are no fixed point of gamma. Therefore, a traditional way out is Kripke's fixed point semantics, which aims to find a partial interpretation of for the truth predicate, which can be seen in some sense as a partial fixed point of the Tarskian operator. So we shift from standard notion of model to partial models when a partial interpretation is just partial functions P, and then to define what means that a sentence is true in a partial model, we need a notion of valuation. And there are many possibilities in this talk. I just focus on supervaluation. For supervaluation, we can define the analogs of the Tarskian operator, the supervaluation operator sigma, which takes as argument as a partial function and is defined just as the intersection of all gamma h for each total hypothesis h, which extends P. And then is a well-known fact that sigma is monotone, and then for every partial interpretation there exists a least fixed point of sigma above P. In particular, there exists the least fixed point of the monotone operator sigma, which is a good candidate as a partial interpretation for truth, since in some sense is a partial local fixed point of the Tarskian operator. However, as Gupta pointed out by his example, in this least fixed point, the three sentences of the examples are not contained in the domain of this least fixed point. A possible way out, there are other fixed points of the supervaluation operator. In particular, there are intrinsic fixed points. This means that fixed point is intrinsic if it is compatible with every other fixed point. There is a complete lattice of such fixed points of sigma. In particular, there exists the largest intrinsic fixed point. And Gupta's example is correctly computed by the greatest fixed point of intrinsic fixed point of sigma. However, the greatest intrinsic fixed point of sigma is also a good candidate as a partial interpretation for truth, but not as good as the least fixed point. The reason is that for the least, from a philosophical point of view, is not as good as the least fixed point, since for the least fixed point we have a way to reach this fixed point from below, just starting from the empty partial interpretation for the truth predicate, then iterating the supervaluation operator, we get a transfinite iteration, transfinite increasing sequences of partial interpretation, which approximates from below the least fixed point. And nothing similar is known or is done for the greatest intrinsic fixed point. So this is the situation about Gupta example and supervaluation. Now let's back to the goal I stated before, and instead of following the informal Gupta's argument, we can look closer to this example I picture the example in this table. So since we have only 3 sentences at work, we have also only 8 possible assignments of truth values to these sentences. Then we can, for each assignment, compute the corresponding evaluation of sentences in an intuitive way. For instance, for the first row, we assume that all the 3 sentences are false. Then, since phi1 says that phi3 is true and phi3 by hypothesis is false, phi1 also is false, phi2 is the negation of phi1 and so is true, and phi3 is true since phi1 is false. And so for the same for all other hypotheses. And we observe that there is one assignment of truth values, P6, which looks like a fixed point of this intuitive operation. Since under evaluation, the truth values assigned to the 3 sentences are left unchanged. So, indeed, this assignment is exactly the right assignment which the informal argument by Gupta led us. And so we can ask for, in this particular case, why this is the right assignment. And there are 2 features of this set of sentences to consider. The first one is that what makes possible to compute the second column in this intuitive way. The fact is that, in principle, to apply Tarski's truth definition, so the Tarskian recursive rule and also the Tarski deconditional, we need an assignment of truth values which is total, since gamma is defined only on total hypotheses. But in fact, actually, all the relevant sentences and the truth values are just displayed in the example. So we can actually compute the truth values of phi1, phi2, and phi3 just knowing the truth values of these very sentences. This is one point. The other point is that not only P6 looks like a fixed point, but in fact is the unique assignment which has this property. So this is these are the 2 features of this sentence which makes Gupta's informal argument possible. And so I try to capture, to formalize these 2 features in the notion of a self-determined set of sentences. The first feature is based on the notion of dependence. So we say that the truth value of a sentence phi depends on a set X if for every 2 total interpretation of the truth predicate which agree on X, the Tarskian operator gives the same truth value for phi. And then we can say that a set X is self-dependent if and only if all sentences in X are in fact dependent on X itself. Except for some slightly different notation, this notion is exactly what is also known as like dependence. And this is the first ingredient. The second is that the notion of solution. We can say that P in our picture was a P6 is a solution if and only if is left unchanged by every total hypothesis H which extends P itself. And it is immediate to see that this condition is actually equivalent to say that that P is a sigma sound where sigma is the supervaluational monotone operator. So we have a strict connection, and we speak later on this. And then with these two ingredients, we can define a set of sentences X to be self-determined if and only if is self-dependent and has a unique solution. So what we can prove about such sets? We can prove these two things at least. So theorem 1, there exists the largest self-determined set, denoted by capital omega. And this is an interesting set since, of course, captures all examples like Gupta, which fall under the notion of self-determined set. And having a unique solution, we can denote this solution by P or omega, and this is a partial interpretation for the truth predicate. However, in itself, P omega is not a satisfactory candidate for truth, since P omega doesn't evaluate even obviously true sentences, like for instance, there exists X such that X is true. However, P omega is a solution, so is a sound for the monotone operator sigma, and then we can also take the least fixed point of a supervaluation above P omega. We denote it by P bar. And second theorem, we can prove that P bar properly extends the least fixed point of sigma, and is included in the greatest intrinsic fixed point of sigma. This makes P bar a possible interesting candidate for a partial interpretation of the truth predicate, since in particular P bar is itself an intrinsic fixed point, and also, of course, his domain extends omega, so P bar is defined on every self-determined set of sentences, so capture every example like Gupta's. And also, in some sense, answer to Gupta's challenge, since P bar can be reached from below, starting with P omega, which is defined in some natural way from the notion of the largest self-determined set. So I can summarize as follows. I started by Gupta's example and the informal notion of the right assignment, and I propose to use having a unique solution as a formalization of the idea of admitting a right assignment, and being self-determined as a property of sets of sentences intended to capture Gupta's example and the like. And then theorem 1 shows that we can consistently combine the local reasoning on different self-determined sets, since we can take the union of these sets and we get a unique solution. And theorem 2 shows that by closing any self-determined set under supervaluation, we can obtain an interesting interpretation for the truth predicate. In particular, the least fixed point of supervaluation above the largest self-determined set is a good candidate for a partial interpretation of the truth predicate, and also provides a possible answer to Gupta's challenge. That's all. Thank you.
Thank you very much. We have 10 minutes for discussions. Yes.
You said that there exists a unique largest self-determined.
Yes.
So can you describe that set?
No, the point is that
what are the sentences that are in this largest self-determined set?
so. Of course, I don't have it. I think that it's not possible to have a syntactic definition of this sentence, since the notion is based on. Sorry, just a moment. The notion of the self-determined set is based on the Lightgate notion of dependence, which is a semantic notion of dependence. So probably is not characterizable in purely syntactical terms. Okay. In the Lightyear's paper, Lightyear wanted to capture, in a sense, sets which are self-determined but also grounded, and so there are the minimal, in a sense, self-determined sets, and this one can be also this one cannot be characterized in purely syntactical terms by an argument already encrypted, since so the notion of dependence is intrinsically semantic. So.
But you mentioned in the next slide that of a sentence that is not in that largest set, like there exists.
Yes, just this is just an example.
This is not in the...
This one is not in since. So the point is that we have a set of sentences and for the notion of dependence, for each possible assignment of these sentences, we compute the truth value of phi, okay? But also for assignments which are not consistent. So if we take a phi is equal to the resist x dx, and this set is self-determined, okay, we can always take two assignments h and g, and we can take the assignment h which make all sentences false, but also outside, okay. And another assignment G, we takes this sentence false and this one and the one sentence true. Okay, and so gamma h of phi will be false, and the gamma h of phi will be true. So it's not possible that since it's true that after one application of gamma, some sentence becomes true. Okay, but when we evaluate this one, this is true. So gamma h exists, there exists ph is true. If and only if there exists phi such that h of phi is equal to 1, is equal to true. Since this is the interpretation of T. So this is just a tacit definition of truth. And so we have take H false on all sentences, and then for H in particular, this is false. While for every other hypothesis, which at least one element true, the hypothesis is true. And so this sentence cannot be in any self-determined set. So we need to close by supervaluation or some other.
Yes. I was just curious, what happens on your proposal with something like Yablo's paradox?
For this sentence,
what becomes true then?
Mm-hmm.
In that case?
So,
I just couldn't compute that.
So I didn't look at the Yablo paradox at all, but I think that is a self-determined set, since intuitively.
So what set is self-determined?
Since intuitively in the Yablo paradox, we display in a sense all relevant sentences, like in Gupta's example, and so we can compute. There is surely there is just one solution.
I don't understand that, because we've got phi 1, phi 2, phi 3. I still don't understand which ones are coming true. I just can't. Just can't work out.
No, sorry. It's just no. sorry. Is it's not self-determined, but it's self-dependent. Okay, but I don't know about. No, I think that there is. But anyway, this is just an analysis of this example, and this is just a starting point. Since also Gupta's example is easy to be modified in order not to be captured by this idea of self-determined set. There are variants in the literature, and so we need a stronger notion of determination, weaker notion of sets to capture these other examples. What I want to convey is the idea to look locally at this example and try to characterize them in some way. So, surely this characterization is not proposed as the best possible.
If you just take the liar's paradox, they said phi1 says that phi1 is false. That's not self-determined.
No, it has no solution.
So it's like this paradox is just a generalization.
Just of course.
Oh, I see. So right.
So the liar puzzle are an example of self-dependent. The liar is self-dependent, so dependent in itself, but it's not has no solution. And the truth teller is self-dependent, but has true solution, and so it's not.
Any other questions? Doesn't seem to be the case, so let's thank the speaker again.
So,